Hello, everybody. Today's lecture will be about the consequences of the replacement theorems. In particular, we're going to answer the question about whether or not the definition of dimension is actually well defined. So before I jump into this, let me just remind you what is dimension and what was the replacement theorem. So if we have a vector space V, then first of all, we call it finite dimensional if it's a span of a finite tuple, and otherwise infinite dimensional. And then if it's finite dimensional, we attach a number to it, the dimension of V, which we write dim V, and this is the number of elements in a basis for V. And so we have to ensure that this does not depend on the choice. And so the first step is this very big result called the replacement theorem. So what does the replacement theorem says? First of all, it says that the size of a linearly independent set in a vector space is always smaller or equal than the size of a spanning set. And then secondly, I can complete a linearly independent set by adding things from the spanning set to obtain a spanning set, and then the size of this tuple will be exactly the same size as of the spanning set. So those are the two results that are presented in the replacement theorem. And so now let's go to the consequences. Oh, I have to scroll down for this to appear on the next page. So corollary 518. And this precisely answers the question whether or not dimension is well defined, because it tells you that if you take a vector space over R and you look at two different bases, they will be of the same size. So let's prove this. And the proof basically goes in the following way. We're going to apply the replacement theorem twice. And so how do we do this? Well, first we apply it to the tuple V1 through Vn as being the linearly independent set, and the second tuple W1 through Wm as being the spanning set, and then the other way around. Yeah. Remember, being a basis means that they're both linearly independent and spanning. So each of them can play either role. And so in this case, we'll see that then this applies that m has to be less or equal than n by this result here that I'm just circling right now. And n has to be less or equal than n. So this is the summary of what we're going to do. Now let it write down in detail. So suppose suppose that V1 through Vn and W1 through Wn are bases for V. We use the replacement theorem twice. So first time, since V1 through Vn is linearly independent and W1 through Wm is a spans V, we can conclude that what? N is less or equal than m. And secondly, since the other way around, W1 through Wm is linearly independent and V1 through Vn spans V, we can also conclude the other inequality. So overall, we get that m is actually equal to n, which finishes this proof. Okay, and then the remark here is that now, with all this, we get that dimension of a vector space is well defined. Great. So let's look at a couple of examples. First of all, if we look at the vector space of just the 0, well then here the empty tuple is a basis, and so the dimension is just 0. Let's go on. Now the dimension of R to the n is, well, n as this standard basis is a basis. Now, well, let's look at m n cross m of R. Well, what is this? Well, the dimension of this is actually n times m, because we have these E1 through En that are a basis for it. And then last but not least, and this is something that might be a little surprising, let's look at the dimension of the polynomials of degree at most n. Well, maybe like the first guess would be it should also be n, but we have to be careful because there's also polynomials of degree 0, and 1 is also in the basis, so you actually get n plus 1. Because what? We have that x to the n minus 1, all the way up to x to the 1. So these are n many already, and then you have to add 1 as a basis. If this is a little confusing, let's look at, let's say, the polynomials of degree at most 3. So the dimension of this is, well, 4, as, well, we get x to the 3, x squared, x, so 3, and then also the constant 1 is a basis. Great. So those are examples of dimensions. Let's go ahead and scroll more down so this appears on the next page. And let's look at theorem 20. This will tell you a little bit about the relationship between spanning and the dimension, a spanning set and a linearly independent set, and how does the length of these correspond to the dimension. Okay, so let's start with a finite dimensional vector space, and let's fix the dimension to be n. Then, well, we know that the basis has size always n, and so a spanning set should be of longer size, yeah, because we always can find a subtuple of a spanning tuple that is a basis. And then furthermore, if this tuple is actually of the right size and it's spanning, then it is already a basis. And so linearly independent is somewhat the other way around. You can never exceed the size of a basis. So a linearly independent set is bounded above, the length of it is bounded above by the basis. And secondly, which also says number 2, it can always be completed to a basis. This is a very important result as well. And then thirdly, here it's kind of a similar result as the second part of number 1, just for linear independence, meaning if you're linearly independent and you're of the right size, meaning size of dimension, then it is already a basis. So this tension, yeah, a maximal linearly independent set was a basis because it's spanning, and a minimal spanning set is also a basis because it will be linearly independent. So let's prove these things. Okay, so suppose that V1 through Vm spans V. Then by a previous theorem, which was theorem 5.16, this said that every spanning set contains a basis. There is a subtuple of v1 through vm that is a basis for v. So the subtuple obviously has shorter size, and it has size at least n. So as, not at least, exactly n. So as dimension of v is equal to n, the subtuple has length n, and so n must be less or equal than n. Furthermore, so now I'm addressing the second part of the result. If m is equal to n, well then the subtuple has to be the whole tuple. And thus it is a basis. This is part number 1. Let's do part number 2. So suppose you have w1 through wn that is linearly independent. And let's fix a basis for v. So a basis we know has size n. So far, so good. Now we're going to use the replacement theorem. So what do we know now? Well, the replacement theorem will tell us that m is less or equal than n. Yeah, so we apply the replacement theorem to the linearly independent set of v1 through vm. So applied to the linearly independent tuple v1 through vm, and the spanning tuple, which is the basis. And the spanning tuple v1 through vn, we have that, well, a linearly independent one is less or equal than the spanning one. And moreover, we can pick things from this basis, attach it to v1 through vm, and make it a spanning set. And there are n minus m vectors let's say bk1 through bkn minus m, such that, well, v1 through vm, bk1 through bkn minus m spans the whole space, so spans v. Now we're going to just rename it to make it kind of look more coherent. Let v m plus I be equal to bki, for I ranging over 1 through n minus m. Then this tuple here above, just by renaming, is v1 through vm, and then bk1 is vm plus 1, and then we go all the way up to vn. Yeah, so it's the same tuple. These two here are the same. They're equal, just different names. So this spans v, yeah, because that's what I just claimed above. And so now by part 1, since this is a spanning tuple of size dimension, this is a basis for v. Then by part 1, alpha is a basis for V. Okay, this is precisely what we wanted to show. Here we can add things such that it becomes a basis. And now part 3 is the m times equals n version of part 2. So I recommend you to look at that in detail by yourself. And this is the end of the proof. Great. Let's go to the next result. Theorem 521. So what does this say? So this studies subspaces of a finite dimensional vector space. So let's start with a finite dimensional vector space V, and we take an arbitrary subspace W. Then we'll claim that, well, this is also finite dimensional, and in particular, the dimension of that subspace cannot exceed the dimension of V. I think that's pretty intuitive that that should happen. And the moreover part here is actually a very important result, and that will be used a lot. So what does it say? Well, it says that if you're a subspace of the same dimension, then you're actually equal. Yeah, so keep this in mind. If you a subspace, yeah, then if your dimension doesn't drop, you actually have to be the same. So you cannot have a proper subspace of the same dimension. And so this is kind of the reason why I let you count functions or sets at the beginning. And I will come back to that later. But what you want to kind of keep in mind is that dimension for a vector space is a little bit like size of a finite set. So I mean by dimension of a finite dimensional vector space. Yeah. So let's see, how does that relate to what I've just said here with this theorem? Well, let's go in the finite set. Let's say you have a set of size 5. You take a subset of size 5. Well, then they have to be the same, right? And so the same happens with dimension. If you have a vector space of dimension 5 and you have a subspace of dimension 5, then they're the same. Okay. So how does this go? We break this up into 2 cases. So the first case is what happens if W is actually the zero vector space. Because what we want to do is, in the second case, is we want to kind of pick out a linear independent set in W. So we start by picking an element that is non-zero. So in the case where W is it's a 0 set, we couldn't do that. So we have to kind of break this up. Well, what happens then? Well, if W is 0, this is actually the rather trivial case, because in this case W is spanned by the empty tuple. Well, thus in particular it's finite dimensional. And well, the dimension of W in this case is 0, which is less or equal than any dimension, because the dimension is always a natural number or 0. And so now the moreover part, so we have to do all of it for both cases. So moreover, if dimension of V is actually equal to the dimension of W, which is 0, then, well, V also has to be the 0 set, because the only vector space that has dimension 0 is the 0, 1. Okay, great. Let's do case 2. So in this case, we assume, that W is not 0. And let's fix the dimension of V to be the natural number n, or 0. So now we start choosing elements. So we can choose W1 in W, which is not 0. Well, what does it tell us? And so this is where this tool comes in that I was talking about before, this lemma saying that the one tuple of a non-zero element is linearly independent. This is by lemma. The number was 510. Yeah, the 510 just says the one tuple is linearly dependent if and only if the element is 0. And what we're going to do is now we're going to keep on adding elements from W to this tuple until we cannot, in a way that it remains linearly independent. So while possible, repeat the following process. Choosing W2 and W such that W1, W2 is linearly independent, then W3 and W such that W1, W2, W3 is linearly independent, and so on. Okay, first thing we have to argue is that this has to come to an end. And well, how does it come to an end? By the dimension of V, yeah, because, okay, we choose them in W, but W is a subspace of V, so all of this also lives in V, so it means that by theorem 522, so the theorem we just proved, we cannot find n plus 1 many linearly independent vectors in V. So since we cannot find n plus 1 many linearly independent vectors in V by theorem 522, this process must stop. Yeah. So in this way, we constructed a tuple W1 through Wm with m less than n, which is linearly independent, and in a way that if you add any other element from W, it becomes dependent. Oops. Okay, and then this should remind you of one result we already had. We had theorem 512. That was what? I mean, obviously you probably don't remember the number, of course, but it had exactly this input. It had the input which start with a linearly independent tuple, and well, adding an element becomes linearly dependent. What does this mean? Well, it means that this element was in the span of the others. Thus, by theorem 512, we have that W is in the span of W1 through Wm for any W in W, which is the same as saying that W is actually a subset of the span of W1 through Wm. Okay? Or in other words, these will span W. So what do I have now? Well, I have a spanning set which is linearly independent, well, that means it's a basis. Well, this implies that the dimension of W is equal to M, which is less or equal than N, which we just saw up here, which is the dimension of V. So we got the first part, and now we have to do the furthermore. Now, what happens if M is equal to N? Yeah, because this was the furthermore part. The furthermore part assume that the dimension of W is equal to the dimension of V. So in this case, M dimension of W, N dimension of V. Well, then by the previous theorem, 520, the third part shows that what? Well, now 523 said what? If I have a linearly independent tuple of size dimension, then it's a basis. Well, now I have this tuple here, W1 through Wm, and M is also the dimension by assumption. So this is actually a basis not only for W, but for V. The tuple W1 through Wm is a basis for V. So V is equal to the span of W1 through Wm, because this is a tuple, hence spanning, which is also equal to W, which finishes this proof. So yeah, let me just go back and tell you why this furthermore part or moreover part is so important. So what we do often is, later on, how do we use it? Well, we use it in a way that we show that that something is a subspace, and then it's of the same dimension, so I can conclude they're the same. So it's used in order to show that two sets, or in this case, two vector spaces, are actually equal to each other. Okay. So now we're coming to the last result of this recorded lecture. Oh, this is not the right one. This is the right one. Proof of this. Okay. Before I start the proof, let me go over the results. So it also studies subspaces. And it says that if you have a finite dimensional vector space and you take a subspace, well, then any basis for the subspace can be extended to a basis of V. So let's do it. Let's start with a basis of W. W1 to Wm. Now, as W1 through Wm is linearly independent, well, where? In W. Well, this being linearly independent doesn't depend on in what space you look at it. Yeah, if you take a bigger space containing these, this will still be a linearly independent set. Spanning is a different thing. Yeah, spanning really depends on the outer space. If you're spanning the subspace, you're not necessarily spanning the bigger space. It is linearly independent in V. Okay, and then, well, this theorem about sizes will tell us now that, well, if you find a linearly independent set in V, it can be extended to a basis of V. So thus, by theorem 520, let me scroll up here, which number it is. Yes, the second part. We can extend this linear independent tuple in V to a basis of V. So this was easy by all the things we've already set up. So this is the end for this recorded lecture, and next time we're going to talk about the rank nullity theorem. Bye-bye.